Okay, welcome to Unit 2. This is our first video in the second unit of our course on digital audio signal processing. And Unit 2 is all about filters, so that's why I use that FILT characterization there, and this is the first video in that. And in this first video, we're going to just characterize certain aspects of filters used for audio. So some of our characterization will be discrete time, and some will be continuous time, because we're going to be talking about some continuous time or analog filters as well, because those play a big role in audio, and for digital audio we need to be able to emulate those classic analog filters. So that's kind of where we're heading, and here is a couple places you can read about the material that I'm talking about in this note set, and I may draw from those sections of those books. So let's first talk about some discrete time filter structures. This is not specific to audio, but will have an impact on how we think about discrete time filters as we apply them in this course. So there's basically two main categories or classes of discrete time filters, and it all boils down to looking at their difference equation, and seeing the structure that's inherent in that. And so the first category is called a recursive filter. And they have feedback. So you look at the difference equation, and I talked about this, I think, in the review material, so you might want to go back and look at that if you haven't already. These are feedback terms. I can't remember, do I show it here? Yes, I do show it. So let's see why we call those feedback terms. So if we were to rewrite this, so I've done two things here. I've written out these summations using summation term symbols, and the other thing is that I've taken all of these terms, which are past outputs, and I've brought them over to the other side, hence the negative term there. And this shows explicitly the idea of feedback. To compute the current output at some time n. Remember, this sum starts at 1, so this is going to be n minus 1, n minus 2, n minus 3. Those are all past output values. So past output values are fed back to create the current. And then let's look at the term here that involves the input samples. So that starts at I equal to 0. So that's x of n is the current time. So it's the current input sample plus a whole bunch of potential past input values. And all of these are weighted by coefficients. And you can see up here I started with a difference equation that had the most advanced output term with a coefficient of 1. We can always do that. If there's something out here, take whatever that is and divide both sides by that, and you get something. It'll change all of these values, coefficient values, and it'll make that 1 out in front. So we can always do that. There's also sometimes you get that the most advanced term there is not n, but maybe n plus 1 or n minus 1 or something like that. We can always re-index this. I don't show that explicitly here, but I do cover that in my signals and systems class. Okay, so that's recursive filters. And then the other big class, remember, two main classes, are non-recursive filters. These have no feedback. The current output is computed depending only on current and past output input samples, no feedback of previous output samples. So that's a non-recursive filter. Here's a block diagram showing the feedback nature of a recursive filter. So these boxes here I show with a D, meaning a unit delay. If you're familiar with the Z transform, which you should be, you might be familiar with putting a Z inverse symbol in there. Either way, it means the same thing. So I'm not going to go into the details of this. You should be familiar with seeing these block diagrams and understanding what they mean. But notice that we have this feedback structure here, and see that I put negatives inside the boxes. Sometimes we leave the negatives off here and then put negative signs next to the arrows coming into the summation. Either way, it works the same way. And then these are the so-called feed-forward terms. So you look at the block diagram, you can quickly identify, this is a recursive filter. And from this difference equation, we can get the transfer function. So in my signals and systems videos, I show how to easily convert between difference equation and transfer function. We get a polynomial in Z inverse over a polynomial in Z inverse. That means this is a rational transfer function. We talked about that back in a note set in Unit 1 when we talked about group delay and phase delay. So maybe you remember that from there. So that's our transfer function. It's a function of Z. That's the thing that connects the input Z transform to the output Z transform under the condition of zero state or zero initial conditions. Then we can convert it into frequency response. Now, just a caution here, this looks like it's the same function, and what I'm really doing is changing Z to omega. This is a little bit of a invalid notation, but it's commonly done, so I'm going to stick with it. I've already shown you that we can really say that this is h of e to the j omega, where we're taking this function and replacing each z by e to the j omega. So that's one way to do it. Another way to do it is to put a superscript z here and then put like a superscript f there. And here I'm abandoning both of those because it's pretty clear from the context. Now, from this, okay, remember I showed you the roadmap of all the different viewpoints of a system. I did that back in the review. And so we have the transfer function giving us a view of the pole zero diagram. So for a recursive filter, we can have poles anywhere and also zeros anywhere. So I'm just showing a few locations of those. And then I put a question mark here at the origin. We may or may not have poles or zeros at the origin, or you might not have anything at all. It depends on the system. But we'll see when we get to non-recursive filters that the only place we'll have poles, and those will be at the origin. And so that's why I put a question mark there, just to kind of call attention to that. So these poles could even be outside the unit circle, in which case the filter would be unstable, and we would not want that. That would not be a usable filter because pretty much any input to that filter the output would just grow without bound, and that's not terribly useful. So we will limit ourselves only to recursive filters that have poles strictly inside the unit circle. So now we can, looking at the pole zero diagram, or just looking at this, or using the freq command, one way or another, we can get the frequency response. So I'm plotting it versus omega divided by pi. That's a trick I like to do. So the 1 here really corresponds to omega being equal to pi. I like that just because MATLAB will just give you nice mile markers, so I can see where pi over 2 is and so forth. If you plot it just versus omega, MATLAB's going to give you some weird hash marks in weird places that don't make any sense. So that's why I do that. And then I'm showing the magnitude of the frequency response. Sometimes we'll be interested in the phase response, but more often than not, we're interested in the magnitude plot. And so one thing you should be familiar with is being able to look at a pole zero diagram and get a rough idea of what the frequency response is going to look like. So you should be able to see these poles here and say, okay, those are going to give me spikes because they're fairly close to the unit circle at frequencies near the angle at which those occur. Not exactly at the angle, but close. And then the other thing we can see here is there's a 0 at that position, and we should be able to figure out that that's going to drag the frequency response down to exactly equal to 0 at the frequency of 0. So remember, this omega axis is really the angle around the unit circle. So make sure you know that. We talked about that before. And also remember that in digital audio, since there is a real-world audio signal involved here, we usually want to look at these filters not on a discrete time frequency axis. We may do that occasionally just to, get a sense for how that looks. But when we really want to assess the filter, we want to know how that filter is going to be operating on the actual frequencies of the actual audio signal. So remember, this is really pi on the omega axis, and pi maps to fs over 2, and minus pi maps to minus fs over 2. And then once you know that, you know where everything else maps. So for example, pi over 2 would map here to fs over 4. So that's the idea. So you should be able to look at the pole zero diagram and kind of get a rough idea, at least for a simple one, what that frequency response looks like. Okay, non-recursive filters, there's no feedback here, just feed forward. They have difference equations that look like this, only one output sample, and then on the right side, linear combination of the current input sample and some potentially past output samples. And then we can write the transfer function. Notice that it's just the coefficients of this in order with powers of z going from z to the 0 down to z to the minus m. Now, we can convert that into what I call z form. So we find the most negative power of z, and we want to clear all the negative powers of z. So let me back this up a little bit, we would multiply by z to the m over z to the m. I haven't done anything because that's really effectively 1, but when I pass this through here, I will clear all the negative exponents on z. And so now I get something that looks like this, all positive exponents on z, and there's that z to the m that I had to put underneath the z to the m that I multiplied in the top to keep everything the same. So now from there we can see, well, I'll show you in just a minute. We can see what the pole zero diagram looks like, but just a little diversion first. We usually go from the z inverse form, not the z form, or I should say the inverse z form, not the z form, to go to the frequency response. So we're just replacing z by e to the j omega to get that, evaluating it on the unit circle just like we normally do. Okay, so now looking at this in the z form of the transfer function, we can see that we're going to have m roots in the denominator. So that would be m poles at the origin. And then we'll have m zeros, and those can be anywhere. I didn't do quite a good job. These two should be complex conjugate pairs, so this one should be straddling the unit circle in the same way that this one did, and maybe these aren't quite aligned, but that's just poor drawing on my part. So non-recursive filters are their nature is completely set by the location of their zeros. In fact, we can show mathematically that any pole or zero at the origin has no effect on the magnitude response of a filter, only affects the phase response. So I talk about that in my signals and systems class, and I think I might have mentioned that and talked about that in the review video for this course. When there's no feedback like this, we get the only place that poles can be is at the origin. They don't have any effect on the magnitude response of the filter, and therefore the filter is always stable because the poles are at the origin, so they're always inside the unit circle. And so now as we walk around from here around, we go from minus pi to pi, and we see a few things happening. We see that these two zeros are on the unit circle, so that causes these so-called nulls, places where the frequency response goes exactly to zero. And then this part's a little bit hard to see. Why does this pop up? It's not because of this pole. Remember, poles at the origin do nothing to affect the nature of the magnitude of the frequency response. It pops up just because there's a place for it to pop up. There's room. So I always like to say that you can think about this coming from the poles and zeros being poles of tenths, infinitely tall poles of tenths, and the zeros being like the stakes that are staking the tent down to the origin or to the surface of the ground. But you're pitching your tent on top of an air hockey table. So if you're not tacking it down, the air hockey table is blowing it up. So that's why we get a little bit of blow up here, and we get a little bit of blow up in this location as well. And then we get a fairly large amount of blow up in between there, just because these zeros are farther from the unit circle and spaced a little bit farther apart. Now, would I be able to draw this exactly from this pole zero diagram? Probably not, but at least I'd get the idea that it's going to pop up here, it's going to be tacked down here, and there will be a couple ups around each of those. But that's the basic idea. Okay, and again, we can link this plot on the discrete time frequency axis, which, like I said, we're more often interested in seeing the actual continuous time equivalent frequency. So that's what, if we put a real continuous time signal into an A to D converter at this sampling rate and run it through this filter, if we plot it on this axis, we can see the effect of this filter on those actual physical continuous time frequencies. Okay, so here is another characterization, IIR versus FIR. And I say here essentially just new names for recursive and non-recursive. And you have to be a little bit careful here, but it's really not a big issue. It's almost always true that IIR is pretty much synonymous with recursive, and FIR is pretty much synonymous with non-recursive. There are a few books that make a distinction between those, but for all practical purposes, they're pretty much interchangeable. So I will pretty much use those interchangeably. But infinite impulse response doesn't mean infinite valued impulse response. It means that the impulse response has infinite duration. It never really goes to zero and stays at zero. Now, yes, it will asymptotically go to zero. So in the real world, once you get out to a certain duration, the impulse response necessarily has to decay down to become negligible and stay negligible. But theoretically, it never really does that. It just asymptotically goes to zero. Whereas a finite duration impulse response literally has a finite duration. It's non-zero only over a finite set of integer indice values. And outside of that, it goes to zero and stays at zero. And it doesn't have to asymptotically go to zero. So like I said, essentially, and there are a few special cases, but we can say if I have a recursive filter with a transfer function that looks like that, we don't need in this course to go through all the details of, doing the partial fraction expansion and looking up terms on Z-transform tables and so forth. But if we were to do that, and here I've just made an assumption just so I can write down a single explicit form, I'm going to assume that there's no repeated poles and that there's no so-called direct terms. So those are things that come out in my signals and systems lecture on this topic. And you can go back there and look, but at least for this case, and it will also be true for even when this isn't true, we'll see that we get things that will last forever. So for this simple case, we just get a sum of a bunch of different exponentials. So the p sub i's are the poles. So those could be complex numbers, and they get raised to the nth power. So remember, for a stable system, all those poles are inside the unit circle. So these poles are all complex numbers whose magnitude is less than 1. And so if you analyze that, you'll see that those terms get smaller and smaller in magnitude as time goes on. So they're decaying, exponentially decaying. And if we handle these other cases, especially if we have any repeated poles, we'll get things that look like this, plus another term that will have like an n p1 to the n out in front. So that'll start to grow a little bit at first because of the n going up, but then eventually this thing wins out. It's trying to go down. So it's a race. You got n going up and you got an exponential going down. Linearly up, exponential down, exponential always wins. So the point I'm trying to make is that for a stable filter, a recursive filter that's stable, the impulse response will decay, but it will never go identically equal to 0. So therefore, IIR. And then a non-recursive filter looking like this, if we take the inverse Z transform of that thing, we're literally saying this is the value of h of n at n equal to 0, and this is the value of of the h of n at n equal to 1, and so on. That just comes by looking at this through the definition of the Z transform, or if you had to, apply the inverse Z transform operator to this and inverse each term using your table together with the delay property and then looking at what you'd get this same thing. This is just a little notation for writing finite duration sequences. We're showing zeros before and zeros after, and then this tells us at what time does it stop being 0. So that's the notational scheme there. So we can see that the impulse response and the coefficients of the transfer function for the FIR case are very easy. In fact, they're just 1-to-1. So very easy to see. So we've got these two different kinds of filters here, IIR and FIR, and we might want to think like, do we care which one we use? What are the pros and cons? So let's look at the IIR case. And it turns out, we'll see this as we go through, but you should have learned a little bit about this in the signals and systems class, that one of the advantages of an IIR filter is that you can get some pretty good filters with a fairly low order filter structure. And so that means that these IIR filters for the same quality, quote unquote, of filter, so that just means it is, maybe closer to an ideal filter than you might get from some other filter. So to get a filter closer to an ideal filter, at least for the magnitude part, you can do it with a fairly low order, and that means it will be computationally efficient. And so that's good. Remember, in our audio signal processing systems, there's usually a lot of stuff going on. Could have lots of filters running could have lots of other stuff running all at the same time. And so don't get fooled and say, well, that filter doesn't take very much computation to do, so why should I worry about complexity? Well, you're adding in complexity from lots of different things. So getting more efficient ways to do things is always a good thing. But perhaps even more importantly, one of the reasons we like these IIR filters is that it's very easy to adjust important characteristics of them. So suppose we want to adjust the cutoff frequency of a low pass filter or adjust the bandwidth of a band pass filter. For IIR filters, we can set those up so that the adjustment is pretty easy to do with just one or two parameters. We'll see that for FIR filters, that's not so easy. You pretty much have to change all of the coefficients in your impulse response. Now, one of the downsides is that IIR filters can't really give you linear phase. And in a lot of audio, that's probably not super important, although there are some scenarios where that might be important. Like, for example, in audio compression, we use banks of filters to break the signal down into smaller little parts and then compress each one of those little parts. So there we often focus on FIR filters with linear phase, but for the most part, we don't worry too much about linear phase. If you think about it this way, all the classic analog audio stuff that everybody loves how it sounds, that was all built with RLC circuits, and those don't have linear phase, so maybe we don't really need linear phase in most audio applications. Okay, so that's IIR. There's some good and maybe some bad, but not that much. Let's look at FIR filters. If we want to get close to an ideal filter, we're going to need a very high order. That means a very large number of coefficients here. So the order of this is B0 versus BM. It's that distance between the indices. So this would be an nth order non-recursive filter. So as the order goes up, the number of coefficients goes up as well. And so as that number of coefficients goes up, in order to compute the output, we need to do that many multiplies and almost that many adds. So as we try to get a better filter, we need a higher order FIR filter, and that will increase the number of multiplies and adds that we have to do. And these filters can get pretty long. To get a nice one, we might need 100 to 200 coefficients, or taps as we call them. And so that can be excessive. And with an IIR, you might be able to get a similarly good filter with just maybe instead of doing 200 multiplies, you might only need to do 4 or 5 or 6 multiplies. So that's a huge difference. The other big thing, as I alluded to above for this, is that it's difficult to adjust certain parameters like the cutoff frequency or the center frequency or the bandwidth of a filter. You pretty much have to adjust all of the filter coefficients in order to get that to happen. So, but the big thing that FIR filters are good for is that we can get linear phase filters. And so that is a scenario that is, like I said, very useful in filter banks used in audio compression. It's also super important in some other areas that we're not interested in. So for non-audio applications like digital communication systems, radar systems, sonar systems, systems where information is conveyed through a series of pulses, linear phase filters are super important in those, but that's not what we're doing here. So we're going to focus mostly on IIR filters. There will be a few times when we'll say, okay, we're being forced to consider an FIR filter, but not because we're trying to design one. It's just that's what we're being forced to try to implement, and we'll talk about that. And that'll show up in the section on reverb. And so that's what I'm saying here. FIR filters are very useful for modeling real reverb impulse responses. And so we really can go to a room and measure its impulse response. Now, technically, that room is an IIR. It will actually theoretically have an impulse response that would last forever. So does that really make sense in the real world? That means that every room is still just ringing from sounds that were in it 10, 20, 30 years ago. Yeah, so that's theory. The reality is, well, at some point things become, physically and practically negligible and they're zero. So even though the room technically has an IIR response, we can truncate it, and now we have an FIR response, and we'll use that as a model for how that room is imparting that reverb sound on some signal. And we'll use that to build systems that will be able to emulate the sound of a room, which is very, very nice. Okay, so that was characterizing recursive versus non-recursive, or IIR versus FIR. So that was talking all about discrete time characteristics. What we're going to talk about for the rest of this note set is true for both continuous time and discrete time. We're not going to be talking about the internal nature of the filters, but just what they do from a frequency response point of view and how we might use those in an audio application. So here's 5 of the classic types of filters. There are some other ones, but these are the main ones that show up. And you've probably seen these 4 before, and you might not have seen an all-pass filter before. So that all-pass filter is a bit odd, but it will be important to us in a lot of applications for audio, and we'll talk about that. But low pass and high pass is pretty straightforward. You've got a cutoff frequency. However you define that, maybe this is where it drops down to 3 dB from up at the top, or some other definition, but we've got a cutoff frequency, and we think that it passes things below that, and it attenuates to varying degrees frequency components that are above that. And the high pass is the exact opposite. Attenuates to some varying degree any frequency below its cutoff, and essentially passes components that are above that. And then we've got band pass. So there we've got a lower edge and an upper edge. And again, those are often defined as where it drops down 3 dB from its passband value. And we're passing frequencies within a certain range. Those are very, very useful in audio, as we'll see as we go through the course, and even just in this note set. And then we have something called a band reject, or probably more commonly called a band stop. So Zolzer in his book DAFX refers to that as a band reject filter, and I like to think of it as a band stop. You've got band pass and band stop. So again, you've got 2 characteristic edge frequencies, and except now we're stopping the components between those edges and passing the components outside that band. So those can sometimes be useful in audio. Maybe there is some region of frequency that is, not particularly nice for what you're trying to do, and you want to notch it out. So that's another name for these, especially when this width is very, very narrow. We might call that a notch filter. So if there's a troubling frequency that is a frequency at which the audio might be feeding back in a live audio application, you can put a notch at that frequency and try to tame that feedback. So that's another way of doing that. So there, the name feedback is a little different from what we were just using. So I think I've covered what I have in these 2. This all pass, that seems like an odd one. We're passing all frequencies equally. Well, I'm showing the magnitude here, which is not really the interesting part. The interest is in the phase, and we'll take a look at that in more detail. And where will we use all pass filters? Well, we're going to use it to build other types of filters, including those used in reverb emulation systems. So digital systems that will mimic the sound of a room. All right, let's give a few more characteristics here for bandpass filters. And what I'm saying here is true for both continuous time and discrete time. So we saw on the previous page FL and FH, and I said, those would probably be defined as the point where the response drops by 3 dB from what it was in the passband. And if we look at the difference between those two, we can define that to be the bandwidth. So I'm using the notation from Zolzer's book. He uses F sub B, but sometimes people use B or BW. So notation is not consistent in any field of engineering. And then we have a center frequency. Now you might be tempted to say, well, the center frequency should be right in the middle of the upper and lower edge. And in some applications that is true, but in audio, it's much more common to define the center frequency this way. Take the product and take the square root. Well, if we were looking at the middle, that would be adding those two things together and dividing by 2. That's a so-called arithmetic average. And if you remember from your studies of math in high school or early college, this is actually called a geometric mean or geometric average. So the geometric mean, if we analyze it, it says, if we take the logarithm, it doesn't really matter what base, but I'm doing 10 here, of the center frequency, and we plug in this definition now using properties of logs. So we've got a power that comes out in front, and we've got a product that turns into a sum of the individual logs. So what we see here is that the geometric mean as a log shows up as the halfway point on a log frequency axis. And so back in the review videos, I showed you how to plot things on log frequency axes. And in audio, those log axes for frequency are extremely important. In fact, we almost always plot things on that axis because it allows us to see the nature over the entire range. 20 hertz up to 20 kilohertz is a really large range, and that's what we need to look at. Okay, so that's kind of interesting. And then that leads us to talking about constant relative bandwidth bandpass filters. So here's the idea. Suppose we have a set of filters, and I guess I should have put some subscripts on here to show that we're talking about each filter in this set of filters, but I didn't do that. It just gets cumbersome to do all that. But for each one of the filters in the set, if we take its bandwidth and divide it by its center frequency, so defined this way, it's equal to some constant, regardless of which of the filters in that set we look at. So that's the idea of a set of constant relative bandwidth bandpass filters. What that means then is that the bandwidth is proportional to the center frequency. So that just comes right from here. We can pull the F sub C over there and we get this relationship. And now I've just subbed in for our definition of center frequency up there. So that means if we look at this set of filters as their center, as we look at filters with different center frequencies, their bandwidth adjusts so that that relationship is maintained. And these are all over the place in audio applications. And we'll look at some applications in just a few slides. But we'll see that that's an important idea. Well, in fact, here we're looking at a picture of this, but later we'll see why we use these and how we use those in certain applications. So these are some pictures out of Zolzer's book. So I'm just referencing that for, just to properly cite something. I try to do that. I don't always get it, but I do try to do that. So here we have a plot versus F in Hertz. So these could be continuous time or discrete time. We don't really know. If they're discrete time, we're just envisioning them on the Hertz, the equivalent Hertz axis, but we do see that we've put this on a log frequency axis. And so here's a set of constant relative bandwidth bandpass filters. So here's one, and let me just draw another one. There's another one. So each one of these little peaks here is the peak position of the of one of those filters in this set. So what do we have? 1, 2, 3, 4, 5, 6, 7, 8. We've got 9 different filters here. The thing that you see is on a log frequency axis, these things each shape looks exactly the same on that log frequency axis. That just comes from how we've defined center frequency and bandwidth and so forth, and that we're making these be constant relative bandwidth. If we were to plot these on a linear frequency, so here we're going from 0 up to 20K. Again, notice on a log frequency axis, we can never show 0. We can show it down as far as you want. The next decade down would be 2. That's how one of the limitations of that. But in audio, we don't really care to go down to 0. But on a linear frequency axis, we can go down to 0. But now look, these don't look the same, but they are this constant relative bandwidth bandpass filters, and that's just because as we go to lower frequencies, the bandwidth has to necessarily get narrower to satisfy that. This is a much easier way to see that. We can't really see that here. The other thing is it's really hard to see what's going down at those low frequencies, right? This is times 10 to the 4th. So even here we're at 2000. That's all the way out here on that axis. So all of this information is all squished in to that region. That's what's hard about looking at things on a linear frequency axis. And that's what's nice about looking at things on a log frequency axis. Okay, so now I just turned around and said how great that was, and now I'm showing them on a linear axis, but I just want to show some characteristics here. So we can have in audio, we commonly have these types of filters with a certain width, and the width is characterized as octave bandpass filters or 1/3 octave bandpass filters. So let's see what we mean by that. So let's look at octave bandpass filters first. That just means that the higher edge is twice the lower edge. That's all that means. And therefore, we can apply our definition, our geometric mean definition for the center frequency. And if we plug this in for FH, we get the square root of 2FL squared. So we get the square root of 2 out in front, and the square root of FL squared is FL. So that's the definition for a octave bandpass filter. So you might wonder, octave, that looks like it should have something to do with 8. Why do I have a 2 there? Well, remember in music, if you're familiar with playing music, going from a C, C all the way up to C, do, re, mi, fa, sol, la, ti, do to do, the fundamental frequency of 2 notes separated by an octave, the fundamental frequencies are double. So that's why this is a double here. So just a weird thing. The octave comes from the fact that there's 8 notes in the standard Western scale. And so that's why musicians call that an octave, and audio engineers just borrowed it but that means in engineering a factor of 2. Okay, 1/3 octave bandpass filters will look like this. And I think on a subsequent slide, I show you something that looks like this on a log frequency axis. Oh, I should also point out, this is a new normalization. It's F relative to Fs. So these are normalized hertz. So that's Fs over 2. Just keep that in mind. Again, I'm just borrowing some slide or some figures from Zolzer's book. All right, let's look at 1/3 octave bandpass filters. Well, now if we define our higher point to be the third root of the square root of 2 rather than 2 times that, it's the cubed root of 2 times FL. And now if we plug that in here for FH and work out the math, it ends up being the sixth root of 2 times FL rather than the square root of 2 times FL. And so here's a plot. I'm just showing 3 of these that make up 1 octave. So we can think about this dashed line as this one curve here. So that's one single 1 octave bandpass filter. And now we're slicing it up into 3 individual filters, each one having a bandwidth that is 1/3 of an octave. And so then we can go through and see that if we start from F1 here, which is the lower edge of the lower of the 3 filters, and we multiply it by that to get up to the edge. So that gives us F2. So this quantity here is F2. Multiply F2 by cubed root of 2, and that takes us up to F3. And then multiply that by the cubed root of 2, and that takes us up to F4. And if you look at these 3 coefficients here, the cubed root of 2 cubed gives us back 2. And so now we see that that spans the width of a 1 octave filter. So this is just a way of more finely slicing things up. So we've got the full octave bandpass filters and the third octave bandpass filters. So these are commonly used in an application called a graphic equalizer. So if we were to build one of these things, we would just make a whole bunch of bandpass filters, and we could make those be octave widths, and then we space them so that they're the lower edge of the next one up is at the upper edge of the one below. We'll see that in just a second. And so we can cover the entire audio range with some number of filters depending upon how wide they are. So we've got a typical scenario where each bandpass filter has a width of an octave. So these are constant bandwidth bandpass filters. And then here's what we do. We take our signal and we pass it through each of those. So we're kind of splitting the signal up into, in this case, n different components. So the signal coming out here is primarily frequencies in that passband. And then we can multiply by a number, and that number could be bigger than 1 or less than 1. So, or equal to 1. So we can either boost those frequency components or cut those frequency components or leave them untouched. So we're slicing it up into a bunch of parts, each part focused to some degree in a certain frequency range, and then we can adjust those, and then we add them all together to create the output. And here's a picture of the controls for a graphic equalizer. I only put this link here just to acknowledge that that's where I got this picture. This is a software-based graphic equalizer. And, here you would have some sort of presets, and this one is showing the so-called flat response, where all of these sliders are set at 0 dB. So remember I said make those bigger than 1 or less than 1. In dB, that would be bigger than 0 or less than 0. So negative dB corresponds to cutting those, attenuating those. So here we've got all of our knobs set at 0 dB, but we could move some of those up. So we might move that up, and we might move that down, and that one up, and maybe that one down, and that one down, and that one up, and that one down. So by adjusting those, we will create some sort of frequency response. And in reality, if I were to think about this and just kind of draw a curve between these things, that might be the frequency response that I would get from this, roughly, anyway. Now, this is an octave based equalizer. So look at the frequencies, the center frequencies of those. They're all related roughly by octaves. So we see that we start off at 16K, an octave below is 8K, 4K, 2K, 1K, 500, 250, 125. And now we break the rule ever so slightly, right? 125 should go to 63.5, I think, or something like that, or 62.5, but it just gets rounded to 64 to make it a nice even number, and then that can be divided by 2 to get to 32. So that's a common little tweak. So that's an octave. And then we have 1/3, or sometimes people just call it a third octave. And so now we have this relationship between our center frequencies. And you can see I've grouped those together down below, and you can see the corresponding centers for the octave, right? So we've got 16 and 8 and 4 and 2 and 1K and 500 and 250 and 125. And now here, this one went to 63 instead of 64. And then 63 divided by 2, well, they went to 31 instead of 32. So just a slight deviation when things get a little funky there. But in each of what was an octave, we actually have 3 controls with 3 different center frequencies. So the width of each of those filters would be 1/3 of an octave. And this one shows some sort of outline of the controls. So an audio engineer would tweak those things up and down, and then can get a graphical view of how they're adjusting the frequency response. That's why it's called a graphic equalizer. It's nice. So the next time you're at a concert or something, take a look at the audio engineer's station where they have the big soundboard, and you'll probably see, these are both software versions, but you'll maybe see some hardware versions of these, and you'll see the knobs, and you can kind of take a look at what they've done with them. They'll often use those to tame certain frequencies, so they might be getting a little bit of a resonance at that frequency, and maybe hear that they're trying to get rid of or tame to some degree, and maybe there's a little bit of dullness at that frequency, and they're trying to improve that. So that's graphic equalizers. We can talk about another kind of filter called a shelving filter. And so what I'm showing you here is a low frequency shelving filter. So a shelving filter has really no stop band. So it's got a band up here where it does nothing, right? This is in dB. So 0 dB, it's neither cutting nor boosting up here. But below that, depending on how I set it, I could get any number of different levels here. So we're showing 1, 2, 3, 4, 5 different adjustments. So it looks like it would be adjusted to a boost of 12 dB, 6 dB, no dB, or a cut of -6 or -12 dB. So if we were, say, adjusted to +6 dB, the overall frequency response would look like this for that shelving filter. You can see it looks like a shelf that we can adjust the height up and down. So that's a low frequency shelving filter. Here's the flip of that, the high frequency shelving filter. Now I'm leaving low frequencies untouched, and I can boost or cut, or leave alone. I could just adjust the control to 0, in which case this shelving filter would be doing nothing at all. So usually there's just a button that allows you to take it out of the circuit in that scenario. So here we're trying to either boost or cut high frequency components. And then we can have something called a peak filter, which kind of is in between those two, right? We had boosting down here, leaving. We had leaving down here and boosting up here. And now we're leaving low and leaving high, and somewhere in the middle we can either boost or cut. So now we have, I should say, I didn't say that. Not only can we adjust which of those, and there could be, a continuum of values between minus 12 and 12, but we can also adjust the cutoff frequency. So the cutoff frequency could move far to the right or far to the left. So a lot of flexibility in doing this. Here we can adjust the booster cut, and again we're just showing 5 possible values for that, but we can also adjust the center frequency, so we can move this whole thing to the right or to the left, or we can adjust the bandwidth. So held fixed at a constant center frequency, we can make this wider or we can make this narrower. So if you make it narrower, you can make a really sharp peak up or a very sharp notch down. So very useful for kind of boosting one small region of frequencies, or probably more often cutting some small region of frequencies where there might be some resonance in the room or something like that. If we use all these together in a cascade, we can come up with something called a parametric equalizer. And it's called a parametric equalizer because you're usually adjusting knobs that you can't look at graphically to see what it's going to do, like we did in a graphic equalizer. So that's just the common name for it. So if we cascade a single low frequency shelf, then follow that with any number of peak filters that we want, and then finally a high frequency shelf. If we cascade all of those together like this, remember this low frequency shelf, its frequency response up here is 0 dB, so it's having no impact on anything that subsequent filters are doing. So that's kind of the idea here. And so now we've got some number of peak filters, so we could have some number of actual peaks there, and then finally the high frequency shelving. Notice that these are in cascade. That's because of the nature of the individual filters, right? They have no stop band. So we pass on things that filter is saying, I'm not going to do anything to it, and then subsequent filters can maybe do something to it. But let's go back and look at the graphic equalizer. That's not a cascade. That's these bandpass filters are in parallel, and then we add their responses together. That's because each one of these has a severe stop band. So it's only letting together certain things and completely stopping the other things. So we have to rely on some other parallel filter to either let those other frequencies through or not. That's a characteristic difference between graphic equalizers and parametric equalizers. And then I just want to finish this note set off with talking about a particular type of filter that's very important in audio, although we won't talk about this any further in this course. But if you do audio, whether it's digital or continuous time, you'll run into these things called weighting filters. And their job is to help you measure things about the audio in a way that's consistent with how your ear is going to assess that. So oftentimes you want to measure how loud is this signal relative to that signal. So your ear and your brain will perceive that loudness one way. But if you just measure like the power of the signal straight away, it's not necessarily going to match up with what your ear is hearing. And that's because human hearing has different sensitivity in different frequency ranges. So your ears are much better at hearing in this range, and lower frequencies and higher frequencies you're less sensitive to. And it's not quite as black and white as that. So if you're interested in that, you can look up the Fletcher-Munson, I think that's the name, Fletcher-Munson effect, or Fletcher-Munson curves, and you can learn more about that. But the basic idea is that people have designed filters to try to roughly capture this essence of human hearing sensitivity across the frequency ranges. So suppose we've got some audio system here, and I'm just showing 3 stages, and maybe we want to measure the loudness at that stage. If we were to just measure like RMS value, we'll talk more about that later, or some other way of measuring volume, we would get an inconsistent measurement. It wouldn't match what our hearing would show. And so we apply a weighting filter before we run it into some sort of power measurement meter. That weighting filter is designed to basically de-emphasize things outside of this range. And here are 2 classic ones. So there are standards that set different weighting filters. You don't have to design your own, and these things are agreed upon. So there's one called the A weighting, and there's one called the CCIR 486 weighting. So CCIR is just a standards committee that, or a standards organization that has established this particular standard for measuring loudness. So you're free to pick which one of these you want to use, or I think there might be a couple other options as well. But you should state which weighting you're using. So you'll often see that in statements. This measurement is A weighted, something like that. We've seen various ways of characterizing filters that are going to be used in audio. We will revisit a lot of these things, particularly those peak filters and shelf filters. We'll see how to build those. But low pass, high pass filters, band pass filters, we're going to see how to build those in discrete time. But before we do that, we're going to have to take a look at what is available as continuous time. Because look, all that classic audio stuff that everybody loves how it sounds, that was all built with continuous time filters. And often, as digital audio signal processors, we're asked to make our digital systems sound like that old analog system. So we need to know how those analog filters work. So in the next set of notes, we'll spend some time just talking about characterizing analog or continuous time filters. And then we'll see in the note set after that how to map those continuous time analog filters into equivalent, quote unquote, pretty close, discrete time filters using something called the bilinear transform. So hopefully you'll check those things out.